Oh, I get it. You don't think we're friends. So now, like Mr. Potato Head, I'm going to give you my angry eyes by looking at the mean value theorem for integrals. So let f be continuous on the closed interval a to b. That means that we know that f is also integrable on that closed interval. Then there exists a c in that closed interval a to b such that the definite integral from a to b of f of x with respect to x is going to actually equal f of c times b minus a. Now do know that that c may not be unique. There may be multiple x values on or in between a and b. That f at that height times b minus a is actually going to be the true value of this definite integral. So we're going to prove this. I've got a little picture here. I'm going to come back to this picture. But basically what we're saying is this. We've got this true, in this case, because f of x is entirely on or above the x-axis, the definite integral from a to b of f of x with respect to x is actually the area of this planar region. And so what we're saying is there exists a c somewhere such that f of c, well this is c, but f of c is the height, right? And this height, f of c, times b minus a, which is the width, basically is nothing more than this box or a rectangle. So what I have is I have an area of a rectangle, and notice that at places there's some extra area up here that wasn't under f of x, and there's some other area up here that was under f of x that's not in the box. But basically I'm saying there's at least one c on or in between a and b such that the base times the height, the base is b minus a, times the height f of c. For that c there is at least one point c in here where this area is actually going to be the same area under f of x here. So what's nice about that is this is for area, but this is true whether it's actually area or whether it's above or below the x-axis, things of that nature too. So let's prove this thing, shall we? So we've got f of little x, x sub little m. That's going to be the minimum height. And we've got f of x sub capital M. That's going to be the absolute maximum height. Of course, because f is continuous on that closed interval, we know there is an absolute max height and an absolute min height. And we also know that little x sub n is in that interval from a to b, and so is x sub capital M, right? So by the theorem that we just proved back when we were friends in the previous video, right, we know that then little m times b minus a is less than or equal to that definite integral from a to b of f of x with respect to x, which is going to be less than or equal to the absolute max height times b minus a. So we do know that. So then what can I do now? I could divide everything through by b minus a. Of course, a can't equal b or you wouldn't have any interval, right? So b is bigger than a, so it's just some positive fixed number. So what I could do is divide everything through by b minus a. So the absolute value, not absolute value, the definite integral from a to b of f of x with respect to x over b minus a, that's just some particular value divided by a constant, right, is less than or equal to m, which is, or greater than or equal to little m, and less than or equal to big M, right? So we do have that. And what's nice about this, why do I know those inequalities hold? Because I'm dividing everything by a positive number since b is bigger than a, right? So b minus a is positive then. And then what I have is I do know that the left side here, this absolute minimum height is actually f evaluated at little x sub little m, right? And this absolute maximum height is f evaluated at x sub capital M, where x sub little m and x sub capital M are both in that interval. So what we're actually going to use here then is then the intermediate value theorem, which leads into the mean value theorem for integrals. But by the intermediate value theorem, I am guaranteed that there will be a c value here that actually, when plugged into f, equals that. So basically I'm guaranteed, I need a blue because I threw it and dropped it. But anyway, this actually equals f of c. So what I'm guaranteed is f of c, there is some c strictly in between that closed interval containing x sub little m and x sub big M. So certainly there exists a c in the closed interval a to b such that f of c by the intermediate value theorem is actually going to equal the definite integral from a to b of f of x with respect to x all over b minus a, right? So then what can we do with that b minus a? Remember, that's an equal sign there. So that actually equals f of c times b minus a. So there's my f of c times b minus a equals the exact value of the definite integral from a to b of f of x with respect to x. So one more thing here besides this visual picture. So once again, you cut through. How can we think of f of little c? Remember, there may be more than one of these that work here, but this, I would consider this to be the average height. So remember, mean value, what does mean mean? That means average. That means add them up and divide by the total number. Well, we have infinitely many things here, right? But mean is average, and value, we're thinking of height value. So this is the average height value theorem for integrals. Okay, and so f of c is basically, if you took all these heights for the f of x curve, of course there's infinitely many, there's at least one point here that would be the average height that would give you the exact same area if you made a rectangle with a base of b minus a and a height of f of c that the true antiderivative from a to b of f of x with respect to x would make. And of course, as an area application, if it's entirely on or above the x-axis, these areas would be exactly the same. So I think we can be friends again.